Today we'll go over the module 19, amino acids and proteins. Let's start. What is the definition of amino acids? It turns out to be amino acids because the keyword acids, they are really organic carboxylic acids. The unique about them, they have amino group, NH2 group. Amino acids are very important components of proteins production in human body. And as you know, these proteins are very, very important in forming muscles, cartilages, hair, nails in humans. In the animals, we have horns, wools, and silk are made of protein as well. Protein can function as hormones and enzymes that regulates this cellular metabolism as well as the digestion. Protein are used in transporting oxygen in the blood and in the muscles. Such proteins are called hemoglobin and myoglobin. Just here an example of how the amino acid looks like. Well, it looks like, if you look at this, the carboxylic acid is there. That's an acid. At the end, it is an carboxylic acid. So we have to have a carboxylic group there. And in this position, which is the first after the carboxylic acid, this carbon called, this one here, called alpha carbon, we have an amino group. See? So therefore, amino carboxylic acid, which is really amino acids, they are amino carboxylic acids. So we have characteristics of this. Here we can look at this, the whole thing here. They have, this is a carboxylic acid, this is amino acids, and this is, this one here is an alpha, correct? Called an alpha here. So this is an alpha here, alpha carbon. And in this alpha carbon, we have a side chain. Here it is, here, look at this side chain. This side chain can extend, can include hydrocarbon chain. Okay, so this is the main block of an amino acid. Carboxylic acid, amino acid, connected to the alpha here in this case, and you have an organic compound connected to this carbon as well. Excuse me. Excuse me. Depending on this side chain R, one can differentiate between the following types and functions of amino acids. So depending on this chain, can one really see different acids. So for the digestion, digestive enzyme, we have an example of the amino acids. We have, or the enzymes, we have amylase, lipase, pepsin, terbinafine. So, and for transport, we have hemoglobin and myoglobin and albumin. And the whole thing is on and on. Hormones, we have insulin and thyroxine. Defense, we have globulins. And for storage, we have other, they are found in egg, in white egg, like albumin. Okay, so, and legume in storage protein. So you can see they have a lot of many functions, these amino acids. And now this is very important. This is really, we can differentiate between different amino acids according to their chain group. So as I said, we'll not touch the carboxylic acid, we'll not touch the amino. We'll look at the chain connected to the alpha carbon, correct? Now, we can differentiate between non-polar aliphatic R group, such as here in this case hydrogen, a methyl group, isopropyl group. So all those are non-polar aliphatic. Now, if we have non-polar aliphatic group, we should have the opposite, which we should have the aliphatic will turn out aromatic, and then the non-polar will be non-polar aromatic. So if you look at this is another R, but this is not aliphatic. If you look at this, these are not aliphatic, these are, we'll say, aromatic. So non-polar aromatic R group. So they are opposite for the aliphatic versus aromatic. So here it is. So aliphatic non-polar, aromatic non-polar. Now, if we have two different aliphatic versus aromatic non-polar R, we are talking about the R attached to the alpha position of the carbon. Alpha position carries out, we said, alpha position carries out the carboxylic acid group and the amino group. And then is this chain, the whole chain is based on this R group, correct? So now we can look at the polar side of this group. We have polar group here, correct? But they are not charged. We have an alcohol here, that's polar. See, an alcohol here, that's all this polar. And we have thiol, that's polar. And we have here an imide. If you look at this is an imide, that's polar. Another imide, that's polar, correct? And if you look at the this one here, looks to me like another imide. So this one here, another imide from another. Now this one looks like amine group, more or less. So if you look at the whole thing, this is polar, but the group here R is not charged. There's no charge. Now we can have polar charge, correct, group, which is positively charged. Look at this. This is positively charged, and positively charged. So here is the R. The R here is positively charged. See here, all this, the group R is positively charged. Can we have negatively charged? Yes. This is the last type. So the last type R can have what? Negative charge polar group. So let's summarize this. How many types? You have 5 types amino acids. Depending on the R group, the chain at the side chain connected to the alpha carbon. This R can be non-polar aliphatic, that's number 1, or non-polar aromatic. That's the second one here, correct? That's the second one. It can be polar, but in this case, polar without charge, correct? As in this case here, polar not charged, or it can be polar positively charged, or polar negatively charged. So 5 types of the amino acid types, correct? And you can see all the names here, like the first one here, the non-polar, correct, aliphatic. This is called glycine, alanine, correct, valine, and it goes leucine. So it goes on and on and on, and all these names. So here it is. This is how is the amino acids coming together and make a protein. So the protein is nothing less than just condensation of, or the combination of several amino acids together through a peptide bond. Remember when we talked about the amides, they do build, they do form the peptide. So we have here two amino acids. This is number 1. This is number 2. Now the unique thing, this will form the carbon terminus. This is a carbon terminus or terminal, and this will form the nitrogen terminal or terminus, correct? And if you connect them together, this here group, the amino group, will come and interact with this carboxylic group. The 2 hydrogen from here, see the 2 hydrogen from here will come and take this oxygen, the 2 hydrogen, because there are 3 hydrogen, will come and take this hydrogen to make up H2O, so produce H2O. And then they will come together and connect themselves, and you can see how nice. This is the first amino acids. I mean, this is the first, this is the second here. This is the first, this is the second here one. And in between this and peptide bond is formed. And that's what's really, now we have a protein. Each one individually or singly considered is amino acid, but when you combine them through a peptide bond, now you speak about protein. Now this is a protein formation. So here is the same thing. We have 3, correct? And here we'll name them even. We'll learn how to name them. Now we have 3 of amino acid, correct? This one here, the first one here, okay, alanine, and this one here, glycine, in the middle, and the third one is serine, so 3. So we connect them again between the, as I said, making a polypeptide bond between the first one, okay, with the second one, and so on, like what we have seen before. So if I go back, we are making the same way between the first and second, and we have it, the third one will be the same thing. So we'll make the same approach here. And now let's have, this is my what? Nitrogen terminal or terminus, and this will be my carbon terminus or terminal. It goes terminus or terminal, it's the same thing. Now, how to name this? This is alanyl, this is glycine, this is serine. How to name this? Well, it turns out to be this amino acid is abbreviated by 3 alphabets, with the first alphabet being capital, correct? Alanyl, I'll put A, capital A, L, A-L-A-N-Y, so A-L-A. So this is abbreviation of alanine. I take the YL out, see the YL has to be taken out, correct? I take the INE out and replace it with YL. So this is alanine, take INE out, add YL to connect it to the second one, to the following one. This is glycine, take the INE out, glycyl. So this one here will be alanyl glycine, and then the last one will be the name of the whole protein, name to according to it. So serine, so the whole thing is serine. So the 3 alphabets, and this is abbreviation how to write them. So this is alanyl glycyl serine. So the last one is serine. We keep it as is. We don't. And remember, we have 3 alphabets, abbreviation of each amino acid. The first one being the capital letter, and the 2 following alphabets are small letters. So this compound now, a protein made of 3 amino acids, called alanine glycyl serine. What types of proteins we have? We have different types of protein. That's according to their structures, cell structures. So we have primary, secondary, tertiary, and quaternary structure. And if you look at this, again, we're repeating ourselves, proteins are made with reaction or condensation or combination of amino acids and making peptides. So if we have formed two peptides, then of two amino acids, correct? We need two amino acids. If we have tripeptides, we need three amino acids. Tetrapeptides, hexapeptides, we need hexapeptides, we need 6 amino acids, and so on. Now let's look at the structure of the amino acids when they come together to make. This is the primary one. This is the secondary one. This is the tertiary one. And you will see, and this is the quaternary one. It's really all about, those are the two keys. I mean, the primary structure is the very important one. It goes in all of them, correct? Primary structure. But then the primary structure can be, can go to the secondary structure because you have alpha helix or you have a beta sheet, correct? And those can be interacting together to form tertiary. So this goes to this, and this goes to this, and this goes to this. So you will see the basic unit is the primary. Then with the arranging space, you can make secondary. And this secondary made of alpha helix and beta sheets. This can interact with all the intermolecular forces among themselves to make tertiary. A tertiary is again can rearrange itself in a very complex manner and produce 4 different chains. So we have one single chain here, one single chain, but it has 2 different arrangement in space. Tertiary, we have a combination of this with intermolecular forces interaction, and here we have quaternary, means 4 units of chains. So let's look at the picture here. This is the primary one. See this very nice primary one. It gives you a number of the amino acids. That's number 1 here, glycine. Alanine is number 25, and it goes here. It gives you just number 5, and then 10, 15, 20, 25. So a long chain. There's nothing about arrangement in space. Nothing is spiral or nothing in a sheet or layer type of a setting. Just a normal sheet. This called primary structure. And remember, you have 25 amino acids. How many peptides you have? Bond. You have 25 peptides. So we have polypeptides, yeah, 25, because we have 25 amino acids connected together and via a peptide bond, correct? So this is the primary structure, very simple one, and believe it or not, this is the basic unit. It can go to this secondary type structure of the protein, but it needs some arrangement. So before we go into the secondary, let's get an example of this primary structure. One of this is called the inositol. Inositol is just, we have 2 primary chains, one called A. This one is A here, and this is B. A is made of 21 amino acids, correct? If you count them, there are 21. And the B are made of 30 amino acids, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, is about 30 carbon atoms, correct? And this one is made of 21 carbon atoms. Anyway, those chain A and B, B is the longer one in insulin, and all those, the unique about them, they are connected through bisulfide or disulfide bond or bridge. So disulfide bond or bridge is connecting those sheets. So we have it here, for example, and we have it here. So they are connecting the chain, and the insulin cannot go nowhere, and therefore insulin here is said to be in this type of setup here because of the disulfide bond called inactive, and is stored in the pancreas. So this form of insulin is stored in pancreas when the time comes and the blood sugar is very high and the insulin is needed to lower this blood sugar, then this sulfide bond will be broken and the two chains are free to move, and therefore insulin is said to be active. So it's said to be active, and it can fight the blood, the high blood sugar. The secondary, as we said, is nothing less mysterious about secondary. It's just the arrangement in space, correct? And two arrangements of the primary chain in a spiral one, in a helix, this is called alpha helix, and in beta helix. So we are getting a protein that's called, has secondary structure. It's nothing mysterious about it. It's just the arrangement in space is different, but it's really primary structure of amino acid combined together to make this primary structure protein. And maybe if I look at this structure here you can see it much better. So this is the helix, alpha helix one, this alpha helix or spiral one, and what's the spiral one is connected to the in alpha position through their hydrogen bond. See the hydrogen bond here, the hydrogen bond here, and there is another one here, another one bond here. Hydrogen bond is keeping this spiral chain stable, and called this chain called alpha helix. Then all this alpha here, correct? And if you go here, this part here, and it's blown up to you here, see this part? This part is see here, this part here is a beta pleated sheet. This is a beta sheet, and you can look, this is a layers, not the spiral, but the layers above each other, and then the hydrogen bond, you can see here the hydrogen bonds in a beta position. So this is what's really happening in the secondary type structure of the proteins. We have alpha helix and beta helix, so they are combined together in the same thing. You will see first alpha helix, and then small tiny amount of it here is the beta sheet. Now if you look at this, secondary protein can be converted into intermediate before it folds spontaneously. So secondary protein structure is used in multiple sequence alignment, which is used in RNA production. So example of this is the structure of collagen. Collagen is the most abundant protein in the human body. It makes the protein of blood vessels, skins, tendons, ligaments, cornea of the eyes, cartilages, and gastrointestinal tract. So if you look at this collagen, it's made of what? Is made of a secondary protein, but it's really woven, is intermixed with each other. It looks like a fiber. So This is the amino acid sequence, correct? This is the amino acid sequence. It goes like this, spiral way, and a little bit of the beta sheet, secondary. They come, and then 3 chains of those or 4 chains of those coming together. See, here they are making fibers. At the end, see, it looks like this. Here it is. And this is called collagen, and this most abundant protein in the human body, made of secondary proteins. The tertiary protein is nothing mysterious about it. It's, if you look at this, it's really secondary one, because here you have the helix, and here you have the helix, and here you can have the sheets. Here you can have the sheet or the primary one. Okay, that's a primary one. Here you can have the sheets, primary one, but this is the helix. So it's nothing new about it. The only new about this, the only new about the tertiary, so it's a combination of primary and secondary. The tertiary is a tertiary protein structure is a combination of primary and secondary, correct? But that's not all the story. The most important thing about the tertiary protein structure is we have the interaction of the group of the intermolecular forces within these chains. Let's look at this. This is a group here, non-polar, correct? This is the dispersion forces, or called London forces, or called van der Waals forces. Not polar, correct? This is not polar. Hydrophobic interaction. We can call this one hydrophobic interaction. Now, if we have hydrophobic interaction, we have hydrophilic or ionic interaction. You can see here, this one here is positive. This one is like negative here. So this one is negative. So you can see this is hydrophilic at the beginning, this hydrophilic here interaction. This is hydrophilic or ionic. Now another form, we have the interaction of the bisulfide bond. This is called bisulfide, and let me just maybe this is SS, bi or disulfide bond or bridge. And then we have here another bond called hydrogen bond. If you look at here, this one here, this one hydrogen bond. The ionic interaction here can also called a salt. It's making a salt, so we can have ionic salt interaction as well. So between, if we have a metal or something, we can have an ionic interaction between this. So tertiary, again, structure of the protein is a combination of primary and secondary. The only unique about it is we have a lot of the interaction of intermolecular forces within these chains, making these chains very stable. So they are really stabilized. The intermolecular forces making the chains very, very stable. And those are the type of intermolecular forces. You have hydrophobic. We went through this together. Go up there. There's the two groups of hydrophobic, this one and this one. Non-polar interaction called van der Waals, hydrophobic, dispersion, intermolecular forces. So they are not, and the opposite of this, the ionic one here, or called hydrophilic. If we have an alcohol, like here, if you have an alcohol group here, and there is another alcohol here group, so we'll have a group of the hydrophilic as well. So, and then hydrophilic, hydrophobic, hydrophilic, two groups are like alcohol groups coming together, correct? And they are hydrophilic, polar. And we have hydrogen bond. We saw the hydrogen bond here. This is the hydrogen bond here. This is the hydrogen bond. This is the hydrogen bond here. Yeah, this is the hydrogen bond. And this is OH with the OH somewhere if there is an OH. Alcohol group together. This will be hydrophilic. And this is hydrogen bond. And if you go to disulfide bridge, we went through this together. That's the disulfide bridge here, or bond. Okay, disulfide bonds. And then you have salt bridge if you have ionic interactions, correct? Ionic interactions there. So now we know that the primary is a very important one. That's the secondary is really made of primary with the different in space arrangement, which can be spiral one called alpha helix or layer one called beta sheet. Now if you have, and then the tertiary one we said is a combination of primary and secondary, correct? But with a lot of intermolecular forces, interaction of intermolecular forces, making the tertiary more stable, correct? Now if we have this tertiary, I can move the tertiary into what? Quaternary structures, correct? I can move this one here to quaternary structure. In this sense, if I have a tertiary structure of amino acids chain and I have a heme, this is the red one, is a heme compound here, correct? This is a polypeptide, beta polypeptide, this tertiary structure. So I can make a quaternary makes of two alphas. This is one, this is two betas, sorry, two betas chain, and two alphas. So we have 4 units. Quaternary means 4. Quaternary structure is made of 4 quaternary chains, and the heme is in between here. You can see trapped in between the alpha and the beta chains. Now this summarizes the whole thing here, and we can maybe blow it up a little bit. You can see it. This is just a normal chain without any special arrangement in space, just a normal chain, okay, of amino acids. This is called primary one. Now if I take this primary chain and make some arrangement in space, like layers staggering the stack on each other, see, then I speak about beta sheet, beta pleated sheet, or if it's arranged in a spiral way called alpha helix, then this primary is turned to be called now secondary. Now if I have those secondary ones combined together with a lot of interaction, with a lot of intermolecular forces interaction, bisulfide, bond, hydrophobic interaction, then what I have, ionic interaction. So all those groups of the intermolecular forces will give me what? Will give me the tertiary one. The tertiary one then, the tertiary one, here it is. The tertiary one can make a quaternary. So if you look at read this, the tertiary protein structure is a 3-dimensional folding pattern of a protein due to the side chain interaction, correct? That's we said about with the interaction with the intermolecular forces. The quaternary protein structure is a protein consisting of more than one amino acid chain. So we have plenty of chain inside interconnected with each other in alpha and beta types. Let me just decreased a little bit. Here is an example of a red blood cell. So if we take one of the here intersection here, small tiny intersection, and we want to blow it up, it blows up to give us all this, whatever inside this. So this is a red blood cell. Blow the small tiny intersection. What is in this intersection? Well, it turns out this is a quaternary, correct? Quaternary protein. We have this green one is beta chain, correct? So this is beta chain, and we have the red one, another beta chain, and we have the alpha chain, the dark red one, and the blue one is alpha chain. So we have 4 chains together, and we have the iron. If you look at the iron here, maybe it's very hard to see. We have the blue one. The iron is the red one, the red behind. Look, I'm looking at this. The iron is, it's small tiny behind what? Behind the blue one. And this blue one here is the heme group. This is a heme group. This is another heme group. Behind it is the iron and the iron. So maybe we'll have to look at the other structure. So this type called hemoglobin, human blood. This type made of 4 different alpha and beta chains, 4 subunits, and you have the heme compound there, and you have the iron there. So if I look at the hemoglobin structure, here it is, very nicely done. You can see this is the hemoglobin molecule. This is just a small tiny intersection of the blood. Here it is. Can you see it? Let's show what's inside. So we have 2 alphas, those purple one, 2 alphas chains, and we have the blue one here, 2 beta chains. And then we have this molecule here. See here, this one here. This molecule here is whatever you see here. This is the heme. This is the whole heme, and the iron is the small tiny red, the same thing you saw in the previous picture, a small tiny. See here, that's the iron here, and the whole thing heme, and this is the iron here. Can you see the iron? The iron is trapped here, and the whole structure is the heme compound. And the hemoglobin is made, as you see, 4 chains, 2 alphas and 2 betas. They have different sequence of amino acids. And again, those subunits, 4 subunits are held together by the different types of interactions we mentioned before. Okay, those intermolecular forces interactions. So each chain, it has to have what? It has to have a heme group that binds to oxygen, correct? All the chain subunits should combine for the hemoglobin to function properly. The hemoglobin is working in the blood vessels. So this is just the structure of the quaternary chain structure, and how is the hemoglobin is fit into this quaternary chain structure. We have hemoglobin, we have myoglobin. Myoglobin is made of a protein that's made of 154 amino acids. So this is a little bit different from whatever we have. So if you have that much of amino acids, you can expect the chains will be huge number of chains, correct? These amino acids form 8. See, that's what we are expecting. Not 4 like the hemoglobin 4. Myoglobin has 8 alpha chains connected together to turns with an oxygen binding site. So there is an oxygen binding site. Myoglobin has a heme group as well, which is responsible for carrying out oxygen molecules to the muscles tissues. Here is just some of the physical properties of amino acids, and just the elemental analysis found, and you will see that they have a good this is the this melting points. So they are really I would say stable There's no negative melting point or something. That's all positive melting points, and some even of them is higher than 300 centigrade Celsius. And those are all you can see. That's the color of this amino acids between brown and yellow. And now we'll go to the last topic of the amino acids and proteins. Let me repeat again, what's protein? Protein is just a combination of a certain amount of amino acids, correct, in sequence. The reaction first, the amino acids, we said it has two sides. One side is the carboxylate ion negative, and one side is the amino group, which will turn ammonium group positive. So those sides can come together and then build an ion like this, called what? This called here positive charge with negatively charged. So this one here, okay, so negative charge, positive charge, as you can see here. Let me just show you here. This is it's called Switter ion. This is our Switter ion. This is negatively charged. This is positively charged, correct? It has carboxylic acid amino group, the carboxylic acid hydrogen, correct? The proton goes and protonate the amino group, and you get this. This is negative, this is positive. Now, it depends of the pH of the solution. If you have too acidic solution, if the acid is you have too acidic, the pH is very, very low, and the solution is said to be acidic, then this type, here it is, this type of structure, the cation is preferred. If you have a very high pH and very basic solution, then the anion is preferred. So you can see this is basic, correct? This is basic here, this is basic preferred, and this is this type here. Oops, sorry. So let me just take it out here. So here it is. The acidic, when the pH is very low and you have high amount of acid present, so very acidic, lower pH, and this is the structure here, correct? And if you have basic, very basic one, then this structure is, the anion is preferred. And you can look at the protonation, you know, and the reverse protonation of the carboxylic acid, of the amino acids, okay, of the amino group. So you can see too much of acid means too much of protons present, and it will protonate the carboxylic acid, and they get deformed in the left. If you have too much base, the base will come and pull out the extra hydrogen from the amino acids, and you get the anion type of structure. The second reaction is amino acids are acids, correct? And because they are acids, they can undergo esterification, making esters. That's always the case. At the end, they are carboxylic acid, regardless. The amino, because they have an alpha carbon of this carboxylic acid, they have an amino group, NH2 amino group. So this one here is amino group, and therefore called amino group. And you can see they can, normal, just a normal esterification. We have an alcohol with carboxylic acid, that's an intermediate here. Then it goes further, correct? And you produce the ester here, correct? So you produce the ester here, which is the OH from the alcohol and the one oxygen from the OH from the carboxylic acid and one H from the alcohol to make the ester here, correct? And here is another example. You can see it. This is your alcohol, aromatic alcohol, and this is our carboxylic acid. So this is diesters, two sides of the molecule. We have two esters groups. Now another reaction is amino acids can react with acetyl chloride. This is phenyl acetyl chloride here, this compound here, can interact with it and can produce an imide, correct? So look at this. This is phenyl acetyl chloride, react with the amino acids. This is an intermediate, and you produce an imide. See here, the peptide bond between carbon and nitrogen, the peptide bond, this is an imide. And here it is, you can see it here. This is an imide, so you can make an imide out of amino acids in presence of they call it amine acetylation reaction. Another reaction, it can react with non-hydrine to get immunoderivatives of amino acids. And this reaction is positively used to identify the amino acids, correct? So the ninhydrine is a compound used in a thin layer TLC, thin layer chromatography, to identify organic compounds. You spray it on the organic compounds that traveled in the mobile solvent, and see how not the time, but how the distance traveled, and then you can, with the known values, you can compare it with the unknown, so you can determine the unknown amino acids or organic compounds. So ninhydrine is used in TLC to identify organic compounds, and ninhydrine will react with amino acid to produce immunoderivatives of amino acids. The last reaction, oxidation. Amino acids can be oxidized, correct? Amino acid that has the thiol, SH, called thiol group. And this is cysteine. Cysteine can be oxidized, and you can make the bisulfide group. You can go back and reduce. So I can go back and reduce. That's a cysteine. So cysteine and cysteine, it has bisulfide group. This one has thiol group. So, and this is the general reaction of thiol with thiol versus, bisulfide. So you can go back and forth. If I oxidize thiol, I get bisulfide. If I reduce bisulfide, I get thiol. And this is, you can see the amino acids is not really affected by the oxidation. However, if I put extreme oxidation in presence of really not oxidizing agent, but pure oxygen and flame and heat, so then I can just decompose amino acids into its carbon dioxide, water, and ammonia. So it will be decomposed in its components came from. There is a reaction of the protein hydrolysis. Well, if we have combined those amino acids into a chain of amino acid called proteins, we can take the protein back to its individual amino acid. Can we? Yes, we can. We can use H2O in acidic medium, acid as a catalyst. We can break down this long chain. Suppose we have 50 amino acids to make a long chain, primary chain, long chain of 50 units of amino acids. Now we have a polypeptide, made of 50 amino acids. I can put H2O and put acidic an acid there, sulfuric acid, for example. Then what I will do in this, or hydrochloric acid, I'll break this chain of 50 amino acids into individual 50 different amino acids. So now we have here, if you look, this is just from looking here, this is one amino acids, correct? This is the second amino acids. If I use H2O in presence of the catalyst, I break it in what? See here? This one here will come, and this is the first one. And this one here, this is the second one. And you can see we can differentiate between them. This is R, this is R prime. So R prime, so we have two amino acids. They were combined together as a protein made of two amino acids. Now they are individual separated amino acids. Denaturing of protein. The protein will be denatured if we use very extreme conditions such as heat, changing the pH, interaction the proteins with organic compounds, adding heavy metals to the protein, or we agitate this protein. All these 5 extreme conditions can affect the stability of the protein and can lead to decomposition if we use too extreme conditions to decomposition of the protein itself. So the 5 factors I just mentioned can affect the biological benefits of the proteins. The extreme conditions, as we said, such the heat, the changing the pH, interaction with organic compounds, addition of heavy metal ions, agitation of the amino acids of the proteins, will destroy and denature the protein and causing the protein to be biologically inactive. Denature can harm both secondary and tertiary, correct? Secondary and tertiary structure. The primary protein is a long chain. It has no arrangement in space, so it should not be affected by this denaturing conditions. But tertiary, because of the arrangement in space, and the secondary, they have arrangement in space, alpha and beta, and the tertiary, they have alpha and beta chains. Those chains will be stripped out, and after the denaturing conditions, they will turn to be what? Primary chain, just a normal long chain, and biologically they are not active. They are said to be inactive because they lost their characteristics, the activity. So, and here is the heat. The heat can destroy the hydrogen bond and the hydrophilic interaction between nonpolar, and it can even destroy the bisulfide bond. Acid and bases, yes, can affect the hydrogen bond and can destroy the salt bridge. Organic compounds, well, organic compounds such as alcohol can destroy hydrogen bond and can destroy the intramolecular hydrogen bonding as well. Heavy metal ions will most of the time will precipitate the disulfide bridges, correct, and make a salt out of them, and will interfere with the polar bonds, so it will make a salt with them. Agitation, mechanical agitation can denature the protein, and it does stress the polypeptide chain and hence destabilize the interaction between the chain. Back to the heavy metals. Heavy metals inside those proteins can consider poisonous. Thank you very much for your attention.